We'll be proving Fermat's little theorem. The theorem that if we have any number a raised to a prime number p, it will be congruent to 1 mod p. Or, in more accessible terms, a to the p minus 1, where p is prime, is always divisible by p. So let's test out some examples. So for example, let's take p is equal to 2. Then what's 5 squared minus 1? Well, that's equal to 24. That definitely divides 2. What's 3 squared minus 1? Well, that's equal to 8. That also pretty much divides 2. Now, of course, 2 is actually an exception, because for even numbers, this doesn't work. But let's try p equals 3, for example. Then this should be infallible. So, for example, wait, state the theorem wrong. Let me check. Oh, crap, I did. I'm dumb. Yeah, so, sorry. That means AP minus A is always divisible by P. So, let's start with an example. P is equal to 2. So, of course, A squared minus A is just equal to, for example, 2 squared minus 2. That's equal to 2. That's definitely divisible by 2. 3 squared minus 3. That's equal to 6. That's definitely divisible by 2. 4 squared minus 4. That's equal to 12. That's also divisible by 2. And you can just keep going. What about A cubed? So A cubed minus A is equal to, well, for example, you have 2 cubed is 8 minus 2. That's 6. That's divisible by 3. 3 cubed minus 3. Well, that should obviously be divisible by 3. 4 cubed minus 4. That's also divisible by 3. And it keeps going. And you can also try 5. 2 to the 5 minus 2 is equal to 30, since it's 32 minus 2. So 3 to the 5 is 243, minus 3 is 240. And 4 to the 5 is equal to 1024, minus 4 is still equal to 1020. So as you can see, all of these are divisible by 5, and we can keep going. But that's not an actual proof. We have to prove that this works for all primes. But if we were just testing this for every single number, for every single prime, we'd be here all day. The rest of the universe, in fact. So, how can we actually prove that this is true? Well, we do it using a little trick called induction. So what is induction, actually? Well, induction basically says, first, let's see if it's true for one specific example. So let's say it's true for k equals 1, for example. Then induction says, well, now let's assume it's true for k and prove that it's true for k plus 1. And if we can do that, then we can replicate this process again. If k equals 1, using this process, we can prove it for k equals 2. Using the fact that it works for k equals 2, we can prove it for k equals 3. And this goes on and on and on and on. So that is how induction works. So, do I have an eraser here? Oh, yeah. How do we use induction in this specific example? Well, we already went over a bunch of examples where this works. But the easiest example to use is, of course, 1 to the p minus 1. That's obviously equal to 0, right? So now, let's assume that p divides k to the p minus k. Now we will prove that this is true for p divides k plus 1 to the p minus k plus 1. Now, why do we do this? Well, let's pretend we plug in k equals 1. We assume it works for k equals 1, which we already know. then we prove it for k equals 2. Then we can plug in k equals 2. We already know it works for k equals 2. Now we can prove it for k equals 3. And the cycle goes on and on. So first, let's use the binomial expansion. So what is k plus 1 to the p? Well, that's equal to k to the p plus, well, k choose 1, which is just k, but we won't expand that. K to the p minus 1 plus k choose 2, k to the p minus 2 plus dot 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 plus k to the k minus 1, which is once again k times k plus 1. So now what happens if we subtract k plus 1? So we get k to the p plus k1, k to the p minus 1 plus k to the p minus 2, and so on and so forth. Wait, oh crap, am I dumb? That's not how the binomial expansion works. K is supposed to be the variable. Dummy. Okay. This is what you get for not bringing lecture notes. Okay. So we get p minus 1, k plus 1. Then we just subtract minus k minus 1. So of course these two cancel out, and we can't really find a good place for minus k, so I'll just put it right here. But we can actually do something miraculous. I'm going to put the minus k right here, actually. But we already assumed that p divides k to the p minus k, meaning this entire part is already divisible by p, which means we can basically just erase it from the equation, and now we only have to prove that this is divisible by p. But wait, we already know by the fact that p choose k has a real-world definition, that is, how many ways there are to choose k objects from a total of p objects. Obviously, there can't be a fractional number of ways to do that, so this always has to be an integer. And furthermore, this is p factorial divided by k factorial times p minus k factorial. Given that if k is greater than or equal to 1, neither of these factorials actually contain the factor of p, and of course there's no p choose 0 here. That means that this entire thing is actually divisible by p. So p choose k is divisible by p. I probably should have used something other than k. P choose n is divisible by p for all 1 is less than or equal to n is less than or equal to p minus 1. So that means that each one of these coefficients is divisible by p, which means for integer k, the rest of this expression is divisible by p as well, which means that we have proved that this entire expression is divisible by p. So in short, what we did was, let me
use the red chuck.
So in short, what we did was we took the base case that 1 to the p minus 1 is equal to 0, since 1 to the p is obviously equal to 1. And of course, 0 is divisible by 1. Or sorry, 0 is divisible by p. So assume that p divides k to the p minus k. We have to prove that p divides k to plus 1 to the p minus k plus 1. So we use the fact that the choose function is always an integer and is always divisible by p, as well as the fact that this turns out to be one of the terms in the binomial expansion minus one of the terms right over here. We can essentially cancel those out, and we just get everything that's right over here. And one more thing, this surplus -1 actually gets canceled out with a +1 in the binomial expansion. Yes, I know it says plus 1, but when you distribute this negative sign, that becomes different. So, since p always divides p choose n for any n between 1 and p minus 1, that means that our final answer is totally divisible by p.